Close your eyes for just a moment. Imagine you are standing still, completely still. The ground beneath your feet is not soil. It is not sand. It is something older than almost anything you have ever touched, a rust-colored powder, fine as flour, born from a world that has been dying for 3 billion years. The sky above you is not blue. It is the color of a bruised peach, pale and enormous. A sky so vast and so empty that the silence pressing down from it feels almost like weight. There is no wind right now. There rarely is this morning. But you can see, in the far distance, a thin ribbon of dust spiraling slowly upward from the plain. A dust devil, hundreds of meters tall, drifting across the desert without a sound you could ever hear. You are on Mars. Not the Mars of science fiction, not the red planet of old adventure stories, with its canals and its ancient civilizations, not the Mars that Hollywood imagined, or that children once drew in crayon on the backs of paper bags. This is the real Mars. And the real Mars is something far stranger, far more haunting, and, if you allow yourself to feel it, far more beautiful than any of those stories ever suggested. Because this world beneath your feet was not always this way. The ground you are standing on, right here, right now, was once the floor of a shallow sea. Warm water lapped against these very rocks. Perhaps 3 billion years ago, if you had stood in exactly this place, you would have been standing knee-deep in a calm, ancient ocean, watching the light of a slightly younger sun play across the surface of moving water. But that world is gone. What replaced it is this: 400 kilometers of silence in every direction. A horizon so flat and so distant that the curve of the planet itself becomes visible if you know where to look. Craters so large they could swallow entire countries. Volcanoes so enormous they pierce the upper atmosphere and create their own weather systems in the clouds above their summits. And underneath all of it, underneath the dust, underneath the frozen regolith, underneath the ancient river valleys and the collapsed lava tubes and the dried lake beds and the long-dead shorelines, there are questions, not small questions. Questions that have kept scientists awake at night for decades. Questions that the most sophisticated machines humanity has ever built have traveled hundreds of millions of kilometers to try to answer. Questions that touch on something so fundamental, so quietly unsettling, that once you hear them, they tend to stay with you. What happened to Mars? Not just in the geological sense, not just the atmosphere, or the water, or the magnetic field, but what happened to the possibility of life on Mars? What happened to 4 billion years of cosmic potential? What does a dead world tell us about how fragile the living ones actually are? And perhaps the most unsettling question of all, a question scientists are only beginning to ask seriously, with careful language and measured tones. In the quiet corners of research papers, is Mars actually dead, or is something still there, waiting, buried beneath the surface of a world the universe seems to have forgotten? Tonight, we are going to walk across ancient Mars together, slowly, without rushing. We are going to cross its great plains and stand at the edge of its canyon systems. We are going to trace the paths of rivers that have not flowed in billions of years. We are going to descend into valleys that were carved by water so long ago that the rocks themselves have forgotten what it felt like to be wet. And along the way, every answer we find is going to open another door. Because that is what Mars does. That is what Mars has always done to the people who study it closely enough. It answers one question, and in the same breath, asks you three more. This is not a lecture. This is not a list of facts to memorize. This is a walk. A slow, quiet, immersive walk across one of the most extraordinary places in the known universe. A world that was once alive with possibility, and that still holds, buried in its ancient dust, some of the deepest secrets our solar system has ever kept. Take a breath. We are already there. Before we take our first steps across the Martian surface, it is worth pausing for a moment to understand what it is we are actually looking for. Because walking across Mars without knowing what to look for would be like walking through a great library without knowing how to read. The information is all around you. Every rock, every ridge, every ancient valley speaks in a language that takes time to understand. And the language of Mars, it turns out, is the language of time. When geologists first began studying the images sent back by the Mariner missions in the 1960s and 1970s, they saw what many expected to see: a barren, crater-covered world, cold, desolate, dead, a world that had never been much more than a cold rock drifting around the sun. But then something strange happened. The more data arrived, the more complicated the story became. Valleys appeared that could only have been carved by flowing liquid. Minerals were identified that could only form in the presence of water. Layers of sediment were discovered that spoke of long periods of stillness, of accumulation, of the slow, patient work of a world that had once been dynamic, active, wet, and scientists began to ask a question that changed everything. How long did this wet period last? The answer, when it came, was staggering. Mars may have had liquid water on its surface, not just briefly, not just for a few thousand years, but possibly for hundreds of millions of years. Perhaps longer. Long enough, in theory, for something more than chemistry to have happened. Long enough, in theory, for life. That is the central mystery we are walking toward today. Not the mystery of whether Mars has life right now, though that is a question we will encounter along the way, but the deeper, quieter mystery. The mystery of what Mars once was, what it could have become. And why, at some point in the distant past, something went catastrophically wrong. Because something did go wrong. Mars today is a world that should not exist in the state it is in. It is too cold for the amount of sunlight it receives. Its atmosphere is too thin to support liquid water, and yet the evidence for ancient rivers and lakes is written in the rock all around us. Its magnetic field is essentially gone, a remnant of what was once a powerful shield that protected everything living on the surface from the radiation of space. And here is what makes Mars so hauntingly different from any other world we have ever studied closely. It did not just change. It did not just evolve the way Earth evolved. It collapsed. It underwent a transformation so radical, so complete, that the world that exists today barely resembles the world that existed 4 billion years ago. What you will discover during this journey is not a simple story. It is a story with layers, literally, layer upon layer of geological time, each one containing a chapter of a history that took billions of years to unfold. A history that begins with a young, warm, wet world and ends with what you see now, a vast, silent desert beneath a pinkish sky. But in between those two endpoints, the warm beginning and the cold now, There is a story of transformation unlike anything we have ever encountered in our exploration of the solar system. A story that, the more closely we examine it, begins to feel uncomfortably familiar. Because Mars was not simply unlucky. Mars was not simply too small or too far from the Sun. The changes that destroyed Mars followed a logic, a sequence of events, each one triggering the next, each one closing a door that could never be reopened. Scientists call this kind of process a cascade. And as we walk across the ancient Martian surface today, we are going to trace that cascade from its beginning to its end. We are going to find the places where the story turned. We are going to stand at the edge of the cliffs and the canyons and the ancient shorelines where the world paused, for a geological moment balanced between two very different futures. One of which it actually took, and one of which it did not. That second path, the one not taken, is perhaps the most extraordinary thing about Mars. Because had things been slightly different, had the dice of planetary formation fallen just a little differently, the world we are about to walk across might not be silent at all. Let us begin. The first thing you notice, walking across the northern lowlands of Mars, is the flatness. Not the gentle rolling flatness of a prairie, not the managed flatness of a desert highway. A flatness so complete, so mathematically perfect in its extent, that the brain initially refuses to process it correctly. You look toward the horizon, and you expect something. A hill, a ridge, a tree, the edge of something, and there is nothing, just the gentle, almost imperceptible curve of the planet itself. This region of Mars is called Vastitas Borealis, the Great Northern Plain, and it covers an area roughly equivalent to the combined land surface of Earth's Pacific Ocean basin. It is, by area, one of the largest unbroken flat surfaces in the entire solar system. And here is the first question it asks you. Simply by existing, why is it so flat? The answer took scientists decades to fully appreciate, and it is more extraordinary than almost anyone initially expected. Vastitas Borealis is not flat because nothing happened here. It is flat because something enormous happened here, and then stopped. The leading theory, developed through decades of careful analysis of the region's topography, its mineral composition, and the subtle gravitational signatures detected from orbiting spacecraft, is that the northern lowlands of Mars were once an ocean. Not a metaphorical ocean, not a network of shallow ponds. An actual ocean. Scientists call it Oceanus Borealis, the Northern Ocean. And at its maximum extent, this ancient body of water may have covered somewhere between 1/3 and 1/2 of the entire surface of Mars. A global ocean so vast that it would have dwarfed anything on Earth. A body of water so deep, in places, that even today's highest resolution radar cannot fully probe its ancient floor. The smoothness you see around you right now is the smoothness of an ocean floor. The fine-grained dust is sediment, ancient, incredibly old sediment that settled slowly through billions of liters of water, layer by patient layer, in a process that took millions of years. And somewhere beneath your feet, beneath that sediment, there are rocks that were once tumbled by waves. But that wasn't the strangest part. Because if there was an ocean here, a real ocean, a persistent ocean, an ocean that lasted long enough to lay down these deep, smooth sediments, then the Mars we are walking across was not merely wet. It was warm. Warm enough for water to remain liquid. Warm enough for an active water cycle, with evaporation and rain and rivers running down from the highlands and returning to refill the sea. Warm enough, some researchers have quietly suggested, for chemistry to become something more. Yet another mystery emerged from the ocean itself: the shorelines. If there was a great northern ocean on ancient Mars, there should be shorelines. And shorelines leave marks, wave-cut platforms, ancient beaches, terraces carved by the slow, patient action of water against rock. Geologists know exactly what to look for, because they have studied the same kinds of marks on Earth and on the floors of dried ancient lakes everywhere. And when scientists looked for Martian shorelines, first in images from orbiting spacecraft, then in detailed topographic maps, then in radar profiles of the ancient terrain, they found something remarkable. They found not one shoreline, but two distinct levels of ancient terrain, separated in elevation by hundreds of meters, each one bearing the hallmarks of prolonged contact with liquid water. Two different shorelines, suggesting two different ocean extents. As if the Martian ocean had once been enormous, then retreated, then perhaps refilled again, the way terrestrial ice ages cause sea levels to rise and fall over thousands of years. Scientists soon discovered that those two shorelines did not quite match the predictions. They ran for thousands of kilometers across the Martian surface, yes, but they were not flat. A shoreline, by definition, should follow a line of equal elevation, the ancient water surface. But the Martian shorelines undulated. They rose and fell by hundreds of meters along their length, tracing a path that no calm ocean would ever produce. What could cause a shoreline to warp like that? The answer, when researchers found it, was both elegant and deeply unsettling. Mars wobbles. Not constantly, not randomly, but over vast timescales, hundreds of millions of years, the rotational axis of Mars shifts dramatically, more dramatically than Earth's axis ever does, because Mars lacks the stabilizing influence of a large moon. Earth's moon keeps our planet's axis relatively steady, holding our axial tilt within a narrow range that is part of what makes Earth's climate livable over geological time. Mars has no such anchor. Its axis can tilt from nearly 0 degrees, almost no seasonal variation at all, to more than 40 degrees, a tilt so extreme it would send polar ice caps migrating toward the equator and turn the tropics into frozen wastelands. And these shifts can happen on timescales of tens of millions of years. Which means that the ancient shorelines of Mars were not warped by strange forces. They were simply moved, physically relocated by the shifting, tilting, wobbling of the planet itself, a planet in the slow process of forgetting what stability feels like. And this discovery opened a door to the next question. If Mars was wobbling that dramatically, if its axis was shifting over those vast timescales, what did that do to its climate? What did that do to its oceans? What did that do to the life, if any existed, that might have been slowly, patiently developing in those ancient warm seas? The answer is where things begin to get complicated. Stand here for a moment. Look north, across the flatness, toward where the ancient ocean once lay. Imagine the reflection of a younger, slightly brighter sun on that water. Imagine clouds, actual water clouds, not the thin ice crystal wisps that occasionally form in today's cold Martian sky, real dense rain-bearing clouds drifting south toward the highlands. Imagine, for just a moment, what this world could have smelled like. There would have been minerals dissolving in the water, chemical reactions playing out across thousands of square kilometers of shallow seafloor, hydrothermal vents perhaps, pumping warm, mineral-rich water up through the ocean floor, creating the same kind of energy-rich environment that scientists believe was the birthplace of life on Earth. And yet Mars is here, today, silent. The ocean is gone. The warmth is gone. The clouds are gone. The magnetic field that once shielded this surface from radiation has been reduced to faint, scattered remnants, islands of magnetism in a sea of exposure. Everything that made Mars potentially habitable has vanished. And the question of why, the question of how a world with this much potential could arrive at this particular silence, is the question we are going to carry with us for the rest of this walk. Because the answer is not simple. And the answer, once you fully understand it, raises an even bigger question. One that is not just about Mars. Leave the northern plain behind and walk south. The ground rises gradually at first, so gradually that you barely notice the change in elevation. But the character of the terrain begins to shift. The smooth, swept quietness of the ancient ocean floor gives way to something older and more textured. The rocks here are more angular. The dust has a different quality, picking up reddish highlights in the low morning light. And ahead, beginning to resolve from the flat distance, something extraordinary comes into view. Channels, not small channels. Not the kind of thing you might overlook or mistake for a geological curiosity. What you are looking at are river valleys, ancient dried river valleys, carved into the Martian highlands with a decisiveness that speaks of enormous volumes of moving water. Some of these channels are wider than the Amazon River at its widest point. Some of them stretch for thousands of kilometers, branching and converging in patterns so similar to terrestrial river systems that the first scientists to see them in high-resolution imagery had to pause and look again to make sure they were seeing Mars correctly. They were. These are the valley networks of the ancient Martian South, and they are, in some ways, the most emotionally striking evidence of Mars's lost past that you can encounter directly, because they are recognizable in a way that abstract data is not. You can stand at the edge of one of these ancient valleys and feel, in a way that bypasses the analytical mind entirely, the presence of the water that once ran here. The shape of the land remembers. But here is the first mystery these valleys present. They are too old. The valley networks of Mars are concentrated in the oldest regions of the planet, terrain that dates back to the Noachian period, the earliest epoch of Martian geological history, which ended approximately 3.5 billion years ago. This is the period when Mars is thought to have been warmest and wettest, and the valleys are exactly what you would expect from that time. What you would not expect, what puzzled researchers for years, is that the valleys stop. Not gradually, not slowly, the way a river system might retreat as a climate grows drier over millions of years. They stop in a way that suggests something more abrupt. A transition. A threshold crossed. After the Noachian period, the record of flowing water becomes sporadic, episodic. There are younger channels carved more recently in geological terms, but they tell a different story. Not the story of a persistent planet-wide water cycle, the story of catastrophic, violent, short-lived floods. Scientists call these outflow channels, and they are something entirely different from the ancient valley networks. The outflow channels of Mars are scars. They are the marks left by events so violent that even billions of years of erosion have not fully erased them. Some of them are the largest known flood features in the solar system, wider than the English Channel, deeper than the Grand Canyon, running for thousands of kilometers across the Martian terrain before emptying into the northern lowlands. What created them? The leading theory is both elegant and slightly terrifying. Beneath the surface of Mars, even in the geological past, there existed vast quantities of water, not liquid water, but water locked in ice. Permafrost, a global layer of frozen ground extending to considerable depth, covering much of the planet like a cold, wet blanket. And then something would destabilize it. A large impact. A volcanic eruption. A shift in the planet's internal heat. Whatever the trigger, the result was always the same. The permafrost would melt, catastrophically, all at once, in a geological moment, releasing vast volumes of liquid water that had nowhere to go except outward and downward, carving enormous channels through whatever rock stood in the way. These floods did not last long. Days, perhaps, weeks. In geological terms, they were essentially instantaneous, a pulse of water, enormous beyond imagination, and then silence again. Scientists soon discovered something even more unsettling about these floods. They may have happened relatively recently, not 3 billion years ago, not during the warm, wet Noachian period when Mars had a thick atmosphere and a functioning water cycle. Some of these catastrophic floods may have occurred within the last few 100 million years, perhaps even within the last few tens of millions of years, which means that even as Mars was becoming the frozen desert we see today, it was still occasionally, catastrophically, violently wet. And this raises the question that has begun to quietly haunt Mars researchers in recent years. Is it still happening? The answer requires us to think about what lies beneath the surface right now, not in the ancient past. Right now, as you stand at the edge of this dried valley, looking at the shapes the ancient water left in the rock, there is still water on Mars, not liquid water at the surface. The atmosphere is far too thin and too cold for that. But ice, enormous quantities of ice. The polar ice caps, which are visible even through amateur telescopes from Earth, are partially made of water ice. And beneath the surface, beneath the dust and the rock and the frozen regolith, there are indications of ice extending to considerable depths across much of the planet. The answer raised an even bigger question. If there is all that water still locked in the Martian subsurface, frozen, waiting, enormous in total volume, what would happen if something warmed it? What would happen if Mars's climate shifted, the way its axis sometimes does? What would happen if a large enough impact delivered enough energy to melt a significant portion of the subsurface ice? What would happen, in other words, if Mars woke up? This is not a purely hypothetical question. Mars's climate does shift, its axis does wobble. Its orbital eccentricity, the degree to which its orbit stretches away from a perfect circle, changes over hundreds of thousands of years, sometimes dramatically increasing the amount of solar energy the planet receives. And some climate models suggest that during periods of high obliquity, when Mars's axis tilts dramatically, the conditions at the surface might become, briefly, marginally suitable for liquid water. Not oceans, not rivers, but perhaps a film of liquid water. Perhaps a trickle, perhaps enough to allow something very small, very patient, very adaptable to survive. Stand at the edge of this ancient valley. Look down at the dry rock at the bottom, where water ran for millions of years and then stopped. Think about what was living in that water, if anything was, and what happened to it when the water disappeared. Where did it go? Did it die? Did it adapt? Did it go down, deeper and deeper into the Martian subsurface following the last warm, wet pockets as the surface grew cold and the atmosphere thinned? Is it still there? That question will follow us for the rest of this walk. Ahead of you, far to the west, something is emerging from the horizon that should not be there. At first, it looks like a cloud, a broad, flat-topped cloud, pale and enormous, sitting impossibly high above the rest of the landscape. But as you walk toward it, and the hours pass and the light changes, you begin to understand that it is not a cloud. It is solid, it is geological, and it is so large that your mind keeps refusing to accept the scale of what you are seeing. You are looking at Olympus Mons, the largest volcano in the solar system. In terms of raw numbers, Olympus Mons is almost impossible to comprehend from the ground. Its base is approximately the size of the state of Arizona, or the entire country of France, depending on which analogy you find more useful. It rises to an altitude of approximately 21 kilometers above the surrounding plain, nearly 2.5 times the height of Mount Everest above sea level on Earth. Its caldera at the summit, the collapsed volcanic crater at its peak, is large enough to contain the entire city of Los Angeles with room to spare. It is so large that if you stood at its base, you would not be able to see the summit. The curvature of the planet would hide it below the horizon. And it is so tall that its summit extends above most of the Martian atmosphere. A climber at the top of Olympus Mons would be, in practical terms, standing in near space. The atmosphere above them would be less than 1% of what it is at the surface. But the strangeness of Olympus Mons is not simply its size. The strangeness is what it tells us about the Martian interior. On Earth, volcanoes like this do not exist. The largest volcanic structure on Earth, the Big Island of Hawaii, measured from its base on the ocean floor, is impressive, but it is nowhere near the scale of Olympus Mons. And the reason Earth does not have a volcano like this is actually a reason for deep geological optimism. Earth's crust moves. The tectonic plates that make up Earth's outer shell are constantly in motion, grinding against each other at subduction zones, separating at mid-ocean ridges, drifting across the face of the planet at roughly the speed a fingernail grows. And because the plates move, a hot spot in the mantle, a place where molten rock pushes up from deep inside the planet, does not stay in one place for long. The plate passes over it, and a chain of volcanic islands or mountains forms, each one progressively older than the last, as the crust carries the old volcanoes away, and a new one forms above the hotspot. This is how Hawaii was made. This is why you can trace the line of the Hawaiian island chain across the Pacific Ocean and read in it the direction of plate movement over millions of years. Mars does not have plate tectonics. Its crust does not move. It is one single, enormous, rigid shell, what geologists call a stagnant lid. And what that means for volcanic activity is exactly what you see ahead of you. The hotspot stays in one place. The magma pushes up through the same vent over and over for billions of years. And with nothing to carry the old volcanic rock away, the mountain simply grows and grows and grows. Scientists soon discovered something extraordinary buried in the rock of Olympus Mons itself. Evidence that it is not entirely extinct. Lava flows have been identified on the flanks of Olympus Mons that are geologically very recent. Not recent in human terms, we are still talking about millions of years. But recent in geological terms, recent enough to suggest that the volcanic system that built this enormous structure may not be entirely cold. The question this raises is immediately obvious. If there is still heat beneath Olympus Mons, if the Martian mantle is still active enough to produce occasional volcanic eruptions, then what does that mean for the rest of the planet? Heat is not just a geological curiosity. Heat is a potential energy source. Heat, in the right geological context, creates hydrothermal systems, places where hot water circulates through rock, dissolving minerals, creating chemical gradients, providing exactly the kind of energy-rich, chemically diverse environment that scientists believe is ideal for life. Hydrothermal vents on Earth support entire ecosystems that have nothing to do with sunlight. Bacteria, archaea, complex organisms, all of them living in total darkness, fed entirely by the chemical energy released by the interaction of hot water and rock. If Mars still has heat, and the evidence increasingly suggests it does, then Mars may still have hydrothermal systems somewhere deep beneath the surface. What happened next surprised researchers. A series of earthquakes, or more precisely, Marsquakes, the InSight lander, which NASA deployed on the Martian surface in 2018, carried the most sensitive seismometer ever sent to another planet. And over the course of its mission, InSight detected hundreds of seismic events, Marsquakes, ranging from small tremors to events significant enough to send seismic waves propagating through the interior of the planet. These Marsquakes confirmed what the volcanic geology already suggested. Mars is not entirely dead inside. Its interior is cooling. Its tectonic activity is vastly reduced from what it was billions of years ago. But it is not zero. The engine that once drove Martian volcanism, built the enormous shield volcanoes, created the hydrothermal systems that may have been the cradle of life on early Mars. That engine is still running, very quietly, very slowly, but still running. And this is where things become even more fascinating, because if the Martian interior is still active, if there is still heat, still geological energy, still the potential for liquid water in the deep subsurface, then the question of life on Mars becomes considerably more complicated than it might initially appear. The surface of Mars is hostile to life in almost every way imaginable. The radiation is intense. The temperature swings are extreme. The atmosphere is so thin, it provides almost no protection from anything. The soil contains perchlorates, toxic chemicals that would be actively harmful to most forms of life we know. But the surface is not the only place to look. Go down through the dust and the frozen regolith. Go down past the ice and the permafrost. Go down to where the pressure increases and the temperature begins to rise, gradually at first, then more decisively, as you approach the still warm interior. Down there, something might be different. Down there, in the deep Martian subsurface, there might be liquid water. Not because the surface is warm enough, but because the rock itself is warm enough. Geothermal heat, combined with the pressure of kilometers of rock above, could maintain pockets of liquid water at temperatures hostile to most surface life but entirely hospitable to certain kinds of extremophiles. On Earth, organisms have been found living in rock fractures more than 3 kilometers below the surface, feeding on chemical energy, with no connection whatsoever to the sunlit world above them. Could something similar survive in the Martian deep subsurface? The honest answer is that we do not know. And we do not know because we have never looked there. All of our Mars missions, every rover, every lander, every seismometer and spectrometer and camera have been surface missions. They have probed the top few meters of Martian soil. They have examined the chemistry of the atmosphere. They have drilled shallow holes and analyzed rock samples. But no mission has ever drilled deep into the Martian interior and looked for water and life where the physics suggests they are most likely to be found. That mission has not yet been built. It has not yet been launched. And in the meantime, Olympus Mons stands above us, impossibly large, a reminder of the enormous geological forces that once shaped this world, and that have not entirely finished with it yet. There is a place on Mars that would stop you completely if you came to it unprepared. It appears without warning as you cross the Tharsis Plateau from the shadow of the great volcanoes. The ground is flat, the horizon wide, the sky its familiar bruised amber, and then, between one footstep and the next, the world simply ends. Not a cliff, not a ridge. An edge. An edge that drops away into a darkness so vast, so deep, so wide, that the far wall, the opposite side, is not visible. It is hidden by the curvature of the planet. The canyon is so enormous that the far rim lies beyond the Martian horizon. This is Valles Marineris, the Valley of Mariner, named for the spacecraft that first revealed its existence to the watching scientists of Earth in the early 1970s, scientists who stared at the images in stunned silence because what they were looking at did not seem real. And the numbers do not make it feel more real. They simply make it more impossible. Valles Marineris stretches for approximately 4,000 kilometers along the Martian equator. That is roughly the distance from Los Angeles to New York City. Its width in places exceeds 600 kilometers. In its deepest sections, it plunges more than 7 kilometers below the surrounding plateau, deeper than the deepest oceanic trenches on Earth, deeper than any canyon in the solar system we have yet found. If you placed the Grand Canyon inside Valles Marineris, it would be a footnote, a minor geological detail, a small side valley in a larger geography that utterly dwarfs anything Earth has produced. But the strangeness of Valles Marineris is not simply its scale. The strangeness is what created it. On Earth, when you think of a canyon, you think of erosion. The Colorado River, over millions of years, cutting steadily downward through the Colorado Plateau, carrying rock away grain by grain until the canyon exists. The process is slow, patient. The story of a canyon is the story of water and time. But the primary mechanism that created Valles Marineris is not erosion. It is not water. It is the ground itself pulling apart. Valles Marineris is, at its core, a tectonic rift, a place where the Martian crust was stretched, stressed, and ultimately fractured, not by colliding tectonic plates, but by the enormous weight and pressure of the Tharsis volcanic region. As magma accumulated beneath Tharsis over billions of years, building the enormous shield volcanoes that rise to our west, the crust surrounding it was bent and stretched. Enormous systems of faults developed, and along those faults, the ground collapsed, in some places by kilometers, creating the vast canyon system we are looking at now. The process is called rifting, and the initial rifting that created Valles Marineris happened billions of years ago. But it did not end there. Scientists soon discovered that water, ancient Mars's abundant, flowing liquid water, found its way into the canyon system and went to work widening and deepening what the rifting had begun. Landslides of extraordinary scale sculpted the canyon walls. Subsurface ice melted and collapsed, creating chaotic terrain at the eastern end of the system, a region called chaos terrain, where the ground looks as if it was literally scrambled by some enormous geological event. And water, pooling on the canyon floor over long periods, left behind the kinds of mineral deposits that speak of prolonged, sustained chemical interaction between liquid and rock. The canyon walls of Valles Marineris are some of the most scientifically valuable real estate on Mars. Because they are a cross-section, a 7-kilometer deep cross-section through billions of years of Martian geological history. Stand at the rim and look down at the layers. Each band of color represents a different geological period. Each stratum tells a different chapter of the same story, a story that begins with volcanic rock from the early planet and works upward through layer after layer of sediment, ice, and chemistry. And somewhere in those layers, scientists suspect, are minerals that could only have formed in the presence of liquid water, specific clays, specific sulfates, specific carbonates that serve as chemical fingerprints of ancient environments that were not just wet, but potentially habitable. The Mars Reconnaissance Orbiter has detected many of these minerals from orbit. The question is what they will tell us when we can actually get down there and examine them up close. Yet another mystery emerged from the depths of the canyon itself. In 2021, radar data from the Mars Express spacecraft revealed something in the deep interior of the canyon system that nobody expected. What appeared to be enormous quantities of water ice, far more than surface observations had suggested, embedded within the canyon walls and floor at depths that had never been directly sampled. This is not ordinary permafrost. The radar signatures suggest ice concentrations so high that some researchers have cautiously described the deposits as essentially pure water ice, buried under a relatively thin layer of dry material. Enough water, in total volume, to fill one of Earth's largest lakes several times over, hidden, waiting, frozen, inside the greatest canyon in the solar system. And then the question becomes almost too obvious to voice. What happens to all of that ice during the periods when Mars's obliquity is high, when the planet's axis tilts dramatically and more sunlight falls on the lower latitudes? What happens to the ice in the canyon walls when the temperature briefly, marginally, fluctuates above the melting point of water? The answer raised an even bigger question. Because there are features on the modern Martian surface, photographed by orbiters in high resolution that look, with an uncomfortable specificity, like the traces of very recent water flow. Recurring slope lineae, arcelle, dark streaks that appear on steep Martian slopes during the warmer seasons and fade during the colder ones. Streaks that extend downslope from local sources and then disappear. Streaks that, when first discovered, generated enormous excitement among researchers because their behavior seemed consistent with liquid water flowing down a hillside. The debate about arcelle has been ongoing for years. Some researchers believe they are caused by liquid water, perhaps briny water, salt saturated enough to remain liquid at temperatures well below the normal freezing point. Others believe they are caused by dry flows, avalanches of dust triggered by temperature changes, mimicking the appearance of water without actually involving any. The debate is not resolved. And the fact that it is not resolved, the fact that there are features on the modern Martian surface that are ambiguous enough to be interpreted as either liquid water or dry dust, and that the best instruments humanity has yet deployed have not been able to definitively distinguish between the two, tells you something important about how much we still do not know. Look down into the canyon. Let your eyes travel down those banded walls, through billion-year-old layers of rock and sediment, to the floor so far below that it is lost in shadow. Whatever is down there, we have not yet reached it. And the fact that we have not yet reached it means that the story of Valles Marineris is, in a very real sense, still unwritten. Step back from the canyon's edge and look up. The sky above Mars is not empty. It never has been, even in the cold present. That delicate salmon amber color you see is not simply an absence of blue. It is the result of fine iron oxide dust suspended in the atmosphere, catching the sunlight and filtering it into this distinctive, slightly alien hue. There is an atmosphere here. It is thin and cold and composed almost entirely of carbon dioxide, but it exists. And the fact that it exists, the fact that even a remnant atmosphere clings to this small, cold, magnetically unprotected world is itself a piece of the story we have been following. Because Mars once had a much thicker atmosphere. How much thicker? The models vary, and the debate among scientists is still active and unresolved, but the evidence points toward an early Martian atmosphere with a pressure somewhere between half and several times Earth's current atmospheric pressure. Not breathable. The composition was still primarily carbon dioxide and nitrogen, without the oxygen that Earth's biology would eventually contribute, but thick enough to create a meaningful greenhouse effect. Thick enough to hold warmth close to the surface, thick enough to allow liquid water not just briefly, but persistently, thick enough, in other words, to make early Mars livable. And then it vanished, not overnight, not in a geological instant, but over hundreds of millions of years, a long, slow, irreversible bleeding away of the atmospheric gases that had once kept the surface warm and wet. Where did the atmosphere go? This is one of the most important questions in planetary science, and it has an answer, or rather several related answers, each one describing a different pathway through which atmospheric gas was lost. The first and most important pathway is a process called sputtering. Sputtering is what happens when energetic particles from the solar wind, a constant stream of charged particles flowing outward from the sun, at speeds of hundreds of kilometers per second, strike the upper atmosphere of a planet and knock atmospheric molecules into space. On Earth, this process is largely prevented by our global magnetic field. The magnetic field acts as a shield, deflecting most of the solar wind around the planet rather than allowing it to strike the atmosphere directly. Earth has maintained this shield for billions of years, and it is a significant reason why Earth still has a substantial atmosphere. Mars lost its global magnetic field. Approximately 4 billion years ago, something changed in the Martian interior. The process, not fully understood even today, involved the cooling and solidifying of the planet's iron core, which reduced and eventually eliminated the convective movement of liquid metal that generates a planetary magnetic field. Without that field, the solar wind had direct access to the Martian atmosphere, and over hundreds of millions of years, particle by particle, molecule by molecule, the solar wind stripped the atmosphere away. The MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, was specifically designed to measure this process, and it has done so in extraordinary detail. MAVEN's measurements have confirmed that the solar wind continues to strip atmosphere from Mars even today, at a rate that, while far slower than the ancient rate, is still measurable, still ongoing. Scientists soon discovered exactly when the critical threshold was crossed. The loss of Mars's magnetic field and the subsequent stripping of its atmosphere did not just cool the surface. It also destroyed the planet's ability to maintain liquid water at the surface in another, more subtle way. With a thin atmosphere, the atmospheric pressure at the surface falls below what physicists call the triple point of water, the pressure at which water can exist simultaneously as ice, liquid, and vapor. Below this pressure, liquid water is not stable. It cannot exist in a steady state at the surface. Ice will sublimate directly to vapor without passing through a liquid phase. Today, the Martian surface pressure averages about 0.6% of Earth's sea level pressure. This is below the triple point of water, which means that if you left a cup of liquid water on the Martian surface today, it would not boil in the conventional sense, and it would not simply freeze. It would do both simultaneously. Part of it would flash immediately to vapor, and part would freeze almost instantly, and the whole process would be over in seconds. Mars did not just lose its water, it lost the conditions under which water could exist. And this is where things become even more fascinating, because the loss of the magnetic field, the thinning of the atmosphere, and the loss of surface water did not happen independently. They were linked. They were part of a cascade, each step making the next one more likely, more severe, more irreversible. The cooling of the core eliminated the magnetic field. The loss of the magnetic field accelerated atmospheric stripping. The thinning atmosphere reduced the greenhouse effect. The reduced greenhouse effect cooled the surface. The cooled surface caused the oceans to begin freezing. The freezing of the surface water reduced volcanic outgassing, which further thinned the atmosphere, which further cooled the surface, which further reduced volcanic activity. A cascade. Each step locking the next one in, closing doors, narrowing possibilities, moving the planet from a warm, complex, dynamic state toward the cold, simple, frozen state it occupies today. Scientists call this a runaway feedback loop. And as they study Mars's history, and as they study the history of Earth, and as they look at the range of planetary environments that exist in the solar system and beyond, they are beginning to understand something quietly sobering. Runaway feedback loops are not rare. They are in some ways a default outcome for rocky planets. The conditions that prevented Earth from following Mars's path, the large moon that stabilizes our axial tilt, the active plate tectonics that recycle atmospheric carbon and maintain a long-term climate-stabilizing feedback, the sustained magnetic field that protects our atmosphere. These are not guaranteed features of rocky planets. They are, from a planetary science perspective, a remarkable combination of circumstances. And the fact that Mars did not have them, the fact that Mars followed a different path, a colder and more permanent path, is perhaps the most important lesson Mars has to teach us. Not a lesson about Mars, a lesson about Earth. We need to talk about Gale Crater. It is midday on our walk now, and the sun, smaller than it appears from Earth, but brighter than you might expect, is casting short shadows from the rocks around us. The dust has a warm quality in this light, copper and ochre and rust, and the air, if you can call it air, is absolutely still. Gale Crater is a 154-kilometer wide impact basin that was formed billions of years ago when something large, a meteorite, an asteroid, perhaps a comet, struck the Martian surface with enough force to excavate a hole that could comfortably contain a small European country. But what makes Gale Crater extraordinary is not the impact itself. What makes Gale Crater extraordinary is what happened inside it afterward. After the impact, over long periods of time, water accumulated in the crater. Not just briefly, not just a flash flood washing through and evaporating within days. Gale Crater accumulated water persistently, repeatedly, over geological time spans that some researchers estimate at hundreds of thousands to perhaps millions of years. And as the water accumulated, sediment settled to the bottom. Layer after layer of sediment, minerals carried in from the surrounding terrain, chemical precipitates formed as the water chemistry changed with the seasons and the epochs. Fine dust from the Martian atmosphere, falling gently through the water column and settling to the crater floor. Over time, these layers built up, and eventually, through the complex interplay of erosion by wind and perhaps later water, the sedimentary mound at the center of Gale Crater became exposed. Layer by layer, billions of years of Martian history. Sitting in the middle of the crater like the world's largest geological textbook. Scientists call it Mount Sharp. Its formal name is Aeolis Mons. And in 2012, the Curiosity rover landed in Gale Crater specifically to read that textbook. What Curiosity found exceeded expectations almost immediately. Within the first months of its mission, the rover identified mudstones, rock formed from the slow settling of fine-grained sediment in still water. The chemistry of these mudstones was extraordinary. They contained sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, the key chemical building blocks of life as we know it. More than that, the chemistry of the ancient lakebed environment was not acidic, not highly saline, not particularly extreme in any direction. It was, in the language of astrobiologists, habitable, not inhabited, not proven to have hosted life, but habitable. Possessing all the chemical ingredients and environmental conditions that on Earth would be perfectly hospitable to microbial life. Yet another mystery emerged from the chemical analysis. Methane. On multiple occasions, Curiosity's instruments detected spikes in methane concentration in the Martian atmosphere near the rover. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, but its presence in the Martian atmosphere carries outsized significance. Because methane is chemically unstable on Mars, in the presence of ultraviolet radiation from the sun, methane molecules are broken apart relatively quickly, within a few hundred years, perhaps less. Which means that if there is methane in the Martian atmosphere today, something is producing it today. Something is generating it now, or very recently, to replace what is constantly being destroyed. On Earth, the vast majority of methane is produced by biology. Bacteria, archaea, living organisms, processing organic compounds and releasing methane as a metabolic byproduct. The belches of cows and the decomposition of organic matter in wetlands and the metabolism of ancient microorganisms deep in the ocean sediments, all of it contributing to Earth's methane cycle, a cycle maintained by life. But methane can also be produced by geology. Certain chemical reactions between hot water and certain kinds of rock can produce methane without any biological input. The process is called serpentinization, and it has been confirmed to occur in various geological settings on Earth and is theoretically possible on Mars. Scientists soon discovered that the methane detections from Curiosity were not consistent. They came and went. They spiked and subsided. They appeared to correlate, in some observations, with the Martian seasons, higher in the warmer months, lower in the cold. This seasonal pattern is puzzling and not fully explained by any current model. Geological methane production should not be strongly seasonal. There is no obvious mechanism by which seasonal temperature changes at the surface should dramatically affect chemical reactions deep in the Martian subsurface. Biological methane production, however, methane produced by microorganisms responding to temperature changes in their environment, could potentially show seasonal patterns. The evidence does not prove biology, not remotely. The methane mystery on Mars remains exactly that, a mystery with multiple possible explanations, none of them yet confirmed. But the fact that the mystery exists, the fact that there is something in the Martian atmosphere behaving in ways that require explanation, is itself significant. Mars is not boring. After decades of study, after rover and orbiter after orbiter and lander after lander, Mars continues to produce anomalies, continues to generate questions, continues to behave in ways that are not fully explained by simple models of a dead, cold, simple world. The Perseverance rover, which landed in Jezero crater in 2021, is operating on a different philosophical premise than Curiosity. While Curiosity was designed to determine whether Mars was ever habitable, a question it answered with a resounding yes, Perseverance is designed to look for evidence of ancient life directly. It is carrying instruments capable of detecting organic molecules at concentrations far lower than anything previously attempted on Mars. It is collecting rock samples, carefully selected, documented, sealed, that are intended to be returned to Earth in a future mission for analysis in laboratories with capabilities that dwarf anything a rover can carry. And it landed in Jezero crater for a specific reason. Jezero was an ancient lake. And not just any ancient lake. It was a lake fed by an ancient river that carried sediment from a large watershed, including rock types known to preserve organic material particularly well. And at the point where that ancient river entered the ancient lake, it deposited a delta, a fan-shaped deposit of sediment that, on Earth, is considered one of the most promising environments for the preservation of ancient biosignatures. If anything ever lived in ancient Mars's lakes, the delta of Jezero crater is one of the best places to look for what it left behind. Perseverance has been looking. The results are suggestive. Organic molecules have been detected. Unusual chemical signatures have been noted. The rocks tell a story of varied, complex chemistry, of changing water conditions, of the kind of environmental diversity that life tends to exploit. But proof? Not yet. The samples are waiting. Sealed in titanium tubes on the Martian surface, they are waiting for a mission that does not yet exist, a technology that has not yet been launched, a journey home that has not yet been planned in detail. And perhaps in those tubes, in those carefully collected fragments of ancient Martian rock, the answer to the oldest question in planetary science is already waiting to be discovered. Or perhaps the tubes will contain extraordinary chemistry and nothing more. Either answer would reshape our understanding of life in the universe. Walk north again, far north. So far north that the season begins to matter in ways it did not near the equator. The Martian poles are extraordinary places. Most people, when they think of Martian ice caps, imagine something similar to Earth's poles, white expanses of frozen water, reflecting sunlight, ringed by a transition zone of tundra and ocean. But the Martian poles are strange in ways that Earth's poles are not, and understanding their strangeness reveals something fundamental about how this planet breathes. The North Polar Cap of Mars is a layered structure, built up over millions of years by the careful alternation of ice and dust. During Martian winters, the polar regions grow as carbon dioxide freezes out of the atmosphere and deposits as dry ice, solid carbon dioxide, like the theatrical fog machines use, but covering an area larger than Greenland. In spring, that seasonal dry ice cap sublimates back to gas. The carbon dioxide returns to the atmosphere, and the permanent water ice cap beneath is revealed. What remains year-round is a cap of water ice roughly 1,000 kilometers across and nearly 3 kilometers thick in places. The volume of water locked in the Martian North Polar Cap alone would, if melted, cover the entire planet in a liquid ocean approximately 30 meters deep. But the truly remarkable thing about the polar cap is not the ice itself. It is what is recorded within it. Drill down into the Martian polar ice, as the Charade and Marsis radar instruments on orbiting spacecraft have effectively done remotely, and you find layers. Thousands of layers. Each one a record of a different time in Martian history, a different climate episode, a different balance between dust and ice deposition. These layers are, in effect, a diary of Martian climate written in ice and dust, stretching back millions of years, recording the great oscillations of the planet's climate as its axis tilted and its orbit stretched, and the balance of its fragile atmosphere shifted over geological time. Studying this diary has revealed something that surprised researchers. Mars's climate is not static. Even today, even now, in the cold modern era, Mars is going through climate cycles, not the extreme cycles of its distant past, not the warm, wet episodes of the Noacian, but cycles nonetheless, oscillations, rhythmic changes in ice distribution and atmospheric density that follow the planet's variations in orbit and axis tilt with a consistency that makes Earth's Milankovitch cycles look almost sedate by comparison. And here is what makes this significant. During some of these cycles, the models predict that parts of Mars's surface become, briefly and marginally, warmer. Not warm by any human standard, not warm enough to make the desert bloom, but warm enough in specific locations, under specific conditions, for ice to melt and refreeze, and perhaps, just perhaps, for a thin film of brine to flow down a slope for a few hours during the warmest part of a Martian afternoon. Scientists soon discovered that this wasn't purely theoretical. The polar layered deposits contain puzzling bright reflections in the radar data, particularly in the South Polar region, where the ice is older and the signals come from different depths. In 2018, a team of researchers analyzing data from the Marsis radar on the Mars Express spacecraft announced a discovery that sent a wave of excitement through the planetary science community. Beneath the south polar ice cap of Mars, at a depth of approximately 1.5 kilometers, they had detected what appeared to be a radar reflection consistent with liquid water. Not a thin film. Not a seep. A lake. A lake approximately 20 kilometers across, sitting beneath 1.5 kilometers of ice, reflecting radar signals with the distinctive signature of liquid water. The announcement was celebrated and immediately questioned. Skeptics raised valid points. The temperatures at that depth, based on current models of Martian geothermal heat flow, should be far too cold for liquid water, even salt-laden water, to remain liquid. For water to be liquid at that depth in that environment, the concentration of dissolved salts would need to be extraordinary, or there would need to be a source of geothermal heat beneath the ice that current models do not account for. The answer raised an even bigger question. Because in 2021 and 2022, further analysis of the Marsis data revealed something unexpected. What had initially appeared to be a single lake reflected beneath the south polar cap appeared to be multiple reflections. Multiple regions showing the same liquid water radar signature, distributed across a larger area than the initial discovery suggested. Were there multiple subglacial lakes beneath the Martian South Pole? Or were the radar signals something else entirely? A geological artifact, a mineral layer, a type of ice with unusual radar properties that was mimicking the signature of liquid water without actually being liquid. The debate continues. Some researchers have proposed that the bright radar reflections could be explained by a particular type of clay mineral, or by very cold ice under specific pressure conditions, rather than by liquid water. Others maintain that liquid water is the most parsimonious explanation, the one that requires the fewest additional assumptions, and that the geothermal heating required to maintain it, while greater than current models predict, is within the range of what the Martian interior might plausibly provide. The resolution of this debate requires better data. It requires a future mission with instruments capable of directly sampling the material at depth, capable of drilling through kilometers of ice, capable of answering a question that no orbiter can definitively resolve from space. It requires, in other words, a mission that does not yet exist. Stand here at the edge of the northern polar cap and look south across the layered ice. The layers stretch away from you like the pages of an enormous book, each one recording a chapter of Martian history, each one waiting to be read. Somewhere beneath the southern pole, something is waiting too. Whether it is water or mineral, liquid or solid, alive or simply chemical, that something is patient. It has been patient for a very long time, And the fact that we cannot yet read it is not a failure of science. It is an invitation. Every step you take on Mars, you are walking on evidence. Not metaphorically. Literally, the ground beneath your boots is composed of minerals that each tell a story of chemistry, of water, of temperature, of time. Mars is not simply red. Mars is a complex palette of geological testimony, if you know how to read the colors. The distinctive red color of Martian soil comes from iron oxide, rust, essentially, iron minerals that were oxidized at some point in the planet's history, turning from their original gray-black into the warm rust tones that give Mars its characteristic appearance. But look more carefully. Look at the colors that lie beneath the surface dust when a rover scrapes it aside, or when a fresher geological exposure reveals the underlying rock, and the palette becomes more complex. Gray basalt from ancient volcanic flows. White calcium sulfate veins threading through older rock, formed when sulfate-rich water percolated through fractures and crystallized. Blue-gray hematite spherules, BB-sized iron concretions that the Opportunity rover found scattered across the surface of Meridiani Planum like cosmic buckshot, forming in water-saturated sediment billions of years ago and nicknamed blueberries by the science team. Green clays, phyllosilicates, detected from orbit in some of the most ancient Martian terrain. Clays that form when water interacts with volcanic rock over long periods and are, on Earth, often associated with environments favorable to microbial life. Orange and yellow sulfates, marking places where acidic, sulfur-rich water once stood and evaporated. Each mineral is a message. Each message requires translation. And reading them together builds a picture of Martian geological history more detailed and more complex than anything scientists imagined before the robotic exploration era began. Yet another mystery emerged from the mineral record. Carbonates. On Earth, carbonates, minerals like limestone and chalk, formed when carbon dioxide dissolves in water and precipitates as calcium carbonate, are extraordinarily abundant. They are everywhere. They underlie vast regions of the landscape. They are the primary long-term sink for carbon dioxide in Earth's climate system, the geological mechanism by which our planet has maintained a relatively stable climate for billions of years, despite changes in solar luminosity and volcanic output. On Mars, carbonates should also be abundant. If Mars had a thick carbon dioxide atmosphere and liquid water on its surface for hundreds of millions of years, the chemistry dictates that enormous quantities of carbonates should have formed. A thick layer of Martian limestone, essentially, blanketing the ancient terrain. But when scientists looked for Martian carbonates, they found very little. Not none, not zero, but dramatically less than the models predicted. A puzzle, a gap between expectation and observation that has not yet been fully explained. Where did the Martian carbon go? Some researchers have proposed that the ancient Martian water was too acidic for carbonate precipitation, that instead of forming limestone, the carbon dioxide in the ancient Martian water remained in solution and was eventually lost, as the water itself was lost. Others have proposed that the carbonates do exist, buried beneath younger volcanic flows or layers of dust, hidden from the remote sensing instruments that orbit the planet, waiting to be discovered by future missions with drilling capabilities. Scientists soon discovered a partial answer, and it raised more questions than it resolved. Carbonate-bearing rock has been detected in specific locations on Mars, most notably in the ancient highlands, and in the ejecta blankets of some large craters that punched through younger surface layers and exposed older material from depth. The carbonates are there. They are simply rare, patchy, and often buried. What this suggests is that the conditions under which Mars's early water interacted with its atmosphere were not constant. They varied. There were periods and places where carbonate formation occurred, conditions that were relatively temperate, with pH values hospitable to mineral precipitation. And there were other periods and places where the conditions were more acidic, more hostile, more disruptive. Mars's early wet history was not uniform. It was episodic, varied, punctuated by volcanic events that injected sulfur dioxide into the atmosphere and turned precipitation acidic, and interspersed with longer, calmer periods when the water chemistry was gentler. What this means for the habitability question is subtle, but important. Life does not thrive in uniform environments. On Earth, life is most abundant and most diverse in environments with gradients, places where different chemical conditions exist in close proximity, where energy flows from one state to another, where temperature or chemistry changes create opportunities for metabolic diversity. Early Mars, with its mix of volcanic inputs and gentle lake environments and hydrothermal systems and periodic acidic pulses, was not a simple world. It was complex, chemically rich, full of gradients and energy flows, and the kind of environmental variety that, on Earth, tends to be associated with biological diversity. The absence of life on early Mars, if it is indeed absent, would require an explanation. And here is where things become even more fascinating, in the most quietly unsettling way: the organic molecules. In 2018, curiosity confirmed what many scientists had suspected but had not previously been able to demonstrate directly. Ancient Martian rock contains organic molecules, not simple organic fragments, easily explained as contamination or abiotic chemistry. Complex organic molecules, thiophenes, benzene rings, long-chain organic compounds, preserved in billion-year-old mudstone. These molecules are not proof of life. Organic chemistry happens without biology. Meteorites regularly deliver organic compounds to planetary surfaces. Interstellar chemistry produces organic molecules in the gas clouds between stars. Abiotic organic synthesis is well established and well understood. But the preservation of complex organics in Martian rock is significant for another reason. It means that if life did exist on early Mars, the chemical evidence of that life might still be there. Preserved, waiting, locked in the ancient sedimentary rock of dried lake beds and river deltas, surviving in a frozen, radiation-shielded, chemically stable state for billions of years. The question is not whether ancient Martian life could have left chemical traces. The question is whether we have looked in the right place, and whether the instruments we have sent to look are sensitive enough to find what we are looking for. The Perseverance rover's sample collection represents humanity's best current attempt to answer this question. The sealed tubes sitting on the Martian surface contain, potentially, the most scientifically valuable material our species has ever set aside for future analysis. And when, not if, but when, those samples are returned to Earth and placed in the most sophisticated analytical instruments ever built, we will know something we have never known before. Whether the chemistry of ancient Mars is simply chemistry, or whether it is something more. Pause for a moment and consider the machines, the extraordinary, patient, lonely machines that humanity has sent to this place, to this exact ground you are walking on over the past half-century. Mariner 4, Viking 1 and 2, Mars Pathfinder, Sojourner, Spirit, Opportunity, Phoenix, Curiosity, Insight, Perseverance, Ingenuity, a dynasty of machines, each generation more sophisticated than the last, each one teaching us something that could not be taught in a laboratory on Earth. Opportunity deserves particular attention. Opportunity landed in January 2004 in a small crater on the flat plains of Meridiani Planum. It was designed to operate for 90 Martian days. It operated for nearly 15 years. 15 years, rolling across the Martian surface on 6 wheels, sending back images and chemical analyses and spectral data, climbing in and out of craters, crossing plains so barren and so flat that photographs taken during its journey have a quality of philosophical loneliness that is difficult to articulate. The rover in its images looks small. The landscape around it is enormous. The sky above is empty. And yet the machine keeps moving, keeps working, keeps looking. During those 15 years, Opportunity drove more than 45 kilometers across the Martian surface, far more than any previous rover mission had achieved. It climbed the inner slopes of craters. It examined meteorites that had lain on the Martian plains for millions of years, undisturbed, polished by wind. It spent years exploring the rim of Endeavour Crater, a 22-kilometer wide impact basin whose ancient rocks contained some of the clearest evidence yet found of early Martian water. And then, in June 2018, a global dust storm, the largest in decades, covered the sun and deprived Opportunity of the solar power it needed to survive. The storm lasted months. The dust slowly settled. The sun returned, but Opportunity did not wake up. NASA engineers sent recovery signals for months. Thousands of commands were transmitted across hundreds of millions of kilometers of empty space, reaching out to a machine that had been the faithful emissary of human curiosity on another world for 15 years. The last signal Opportunity ever sent, before the storm silenced it permanently, was decoded and translated by engineers at JPL. It contained routine data about the rover's power levels and status, but one member of the team described it differently. In the telemetry, the rover was reporting that the sky had gone dark, that its battery was running low, and that it was becoming difficult to see. Whether you read poetry into that or not is a matter of personal temperament. But something about the image stays with you. Scientists soon discovered that the same dust storm that ended Opportunity's mission provided one of the most valuable data sets ever collected about the Martian atmosphere. The storm, visible from Earth through amateur telescopes, observed simultaneously by every spacecraft orbiting Mars, provided an unprecedented opportunity to study the global dust cycle that shapes Martian climate. What the data revealed was striking. During a global dust storm, the Martian atmosphere warms significantly, not at the surface, where temperatures actually drop as sunlight is blocked by the dust, but at altitude, in the upper atmosphere, where the dust absorbs solar radiation and creates a vast warm layer that alters atmospheric circulation patterns. These circulation changes, in turn, affect how quickly atmospheric gases escape to space, how the polar ice caps evolve during the storm, and how the surface temperature changes across different latitudes. The study of Martian dust storms is, in other words, not just atmospheric science. It is the study of a climate system so extreme, so dynamically active, despite its apparent simplicity, that it continues to produce surprises. What happened next surprised researchers working with the InSight lander. InSight arrived on Mars in November 2018, just as Opportunity's story was ending. Its mission was different from any previous Mars lander, not to study the surface, not to look for water or biosignatures, but to listen. To listen to the interior of the planet. Using an extraordinarily sensitive seismometer shielded from the Martian wind by a dome that InSight deployed onto the surface, the lander spent more than 3 years recording the faint trembling of the Martian crust, Marsquakes, distant impacts, the acoustic signatures of dust devils passing overhead. The seismic data revealed a Martian interior with more complexity than expected. The crust was thicker than most models had predicted, somewhere between 20 and 37 kilometers thick, with significant lateral variation. The mantle beneath the crust was not perfectly uniform, and the core, the iron-rich heart of the planet, whose dynamics are ultimately responsible for the presence or absence of a global magnetic field, was found to be considerably larger than previous estimates, approximately 1,830 kilometers in radius, making it proportionally larger relative to the planet as a whole than Earth's core. And crucially, the data suggested that the Martian core is liquid, not solid. Liquid, which means that the conditions for generating a magnetic field through convection, the churning of liquid metal that creates Earth's protective shield, are potentially still present on Mars. The materials are there. The liquid iron is there. What is apparently absent is the vigor of convection necessary to sustain a dynamo effect. Whether that convection could be reignited under any circumstances, whether the Martian magnetic field is permanently extinct or merely dormant, is a question that the InSight data has not definitively answered. But it has made the question considerably more interesting. Yet another mystery emerged from the seismic record. Among the hundreds of Marsquakes InSight recorded, 2 events stood out. 2 large Marsquakes, larger than anything else in the dataset, that occurred during the final months of InSight's operational life. These events generated seismic waves energetic enough to probe the deep interior of the planet, to travel through the core itself and emerge on the far side, providing the first direct measurements of what lies at the very center of Mars. The data from these 2 events refined the picture of the Martian core significantly, but they also raised a new question that the science team is still working to answer. The seismic velocity through the Martian core was slightly different from what the pre-existing models predicted, in ways that suggest the composition of the core may be somewhat more complex than a simple iron-nickel alloy. There may be significant quantities of lighter elements, hydrogen, carbon, sulfur, oxygen, mixed into the Martian core. And the presence of lighter elements affects not just the core's physical properties, but its thermal evolution. It affects how quickly the core cools, whether it might eventually solidify and develop an inner solid region the way Earth's core has. What the conditions at the core mantle boundary look like, and what they imply for the deep interior's ability to drive geological processes at the surface. Mars is still telling its story. The machines we sent are listening, and what they are hearing is not the silence of a dead world. It is the sound of a world in transition, slow, patient, planetary scale transition, moving through a phase of its existence that we happen to arrive just in time to witness. The light is changing now. On Mars, the afternoon sun moves differently from how it appears from Earth. The planet's rotational period is only slightly longer than Earth's day, 24 hours and 37 minutes. But the quality of the light here has its own character. A slightly redder, slightly more diffuse quality as the sun descends toward the western horizon. A softening of shadows, a deepening of the copper and ochre tones in the dust around your feet. The day on Mars is almost over, and it is time to look forward rather than backward. Time to stand in the ancient dust and consider what Mars will be, not in the geological deep future, but in the human near future. Because humans are going to Mars. Not as a vague aspiration, not as a science fiction scenario, as an engineering project that is, by any reasonable assessment of the current trajectory, within the lifespan of people who are alive today. The question is not really whether it will happen. The question is what it will mean for the science, for the politics, for the ethics, and for the long story of Mars that we have been tracing through these ancient plains and canyons and polar caps. The scientific arguments for human exploration of Mars are compelling and well established. The most powerful is simply this: a geologist with a hammer or a biologist with a microscope is orders of magnitude more capable than any robotic system we can currently design. Not because robots are bad, they are extraordinary, and the contributions of the robotic missions to our understanding of Mars are incalculable, but because the complexity and flexibility of human judgment in a rich geological environment outpaces what we can encode in software and hardware by a factor that is difficult to quantify but impossible to overlook. A trained geologist walking along the rim of Jezero crater would, within a day of fieldwork, likely gather more scientifically critical observations than a rover can achieve in months. This is not a criticism of rovers. It is a recognition of the extraordinary adaptability of the human mind in an empirical environment. And the question of Martian life, the question that has threaded through everything we have discussed today, may ultimately require human presence to answer definitively. The locations most likely to harbor ancient biosignatures and the locations most likely to harbor extant life are locations that are difficult or impossible to access robotically. The deep subsurface, hydrothermal systems in volcanically active regions, the underside of polar ice in the southern cap. Scientists soon discovered that planning for human Mars missions was itself generating new scientific questions. When engineers began designing the life support systems needed to sustain humans on the Martian surface for extended periods, they confronted the challenge of in situ resource utilization, using Martian resources to generate oxygen, water, and fuel rather than transporting everything from Earth. The MOXIE experiment on Perseverance was a direct test of one such technology, a small box that demonstrated the ability to generate oxygen from the Martian atmosphere by electrolyzing carbon dioxide. The experiment worked. Small quantities of breathable oxygen were produced on the surface of Mars using hardware no larger than a car battery. The technology exists in principle. What does not yet exist is the political will and economic framework to deploy it at the scale needed to support human presence. But the answer raised an even bigger question. What are the ethical boundaries of Mars exploration? This is not a question that gets enough public attention, but it is one that planetary protection scientists take with complete seriousness. If there is life on Mars, microbial life, extremophile life, ancient biosignatures in the deep subsurface, then human missions to Mars carry a risk that no robotic mission can match. The risk of contaminating the Martian environment with Earth biology. Humans are walking, breathing ecosystems. We shed skin cells and hair and exhale microorganisms with every breath. The idea of keeping a human Mars mission sterile, in the way we can sterilize a robotic spacecraft before launch, is essentially impossible with current technology. Which means that if we send humans to Mars before we have definitively determined whether life exists there, we risk contaminating the evidence. We risk making the question of Martian life permanently unanswerable, because any biology we find after human missions could be dismissed as Earth contamination. The scientific and ethical tension here is real. How do we balance the scientific urgency of answering the life question with the scientific risk of destroying the evidence by acting too quickly? How do we weigh the long-term human benefit of a multi-planetary civilization against the potential cost of introducing Earth biology to an environment that has evolved in complete isolation for 4 billion years? These are not rhetorical questions. They are questions that will need real answers before the first crewed Mars mission launches. And here is where things become even more fascinating in a way that very few people fully appreciate. The question of planetary protection is not just about whether Earth life will harm Martian life. It is about the possibility that it might not. Because if there is microbial life in the Martian subsurface, ancient, adapted, patient, it has been adapting to Martian conditions for billions of years. It has survived radiation levels that would kill most Earth organisms. It has survived temperature extremes that would shock most terrestrial biology. It has metabolized using energy sources and chemical substrates that are unavailable or rare on Earth. Meeting Earth microorganisms for the first time would be, for Martian life, an entirely novel experience. And the outcome of that meeting, who outcompetes whom, who adapts, who survives, what metabolic strategies prove most robust in the Martian environment, is completely unpredictable. The history of ecology on Earth is full of cautionary tales about what happens when species that evolved in isolation encounter each other for the first time. Islands stripped of their native wildlife by introduced predators, invasive plants overrunning ecosystems that had no defenses against them. The outcomes are rarely benign. On a planetary scale, with organisms representing 4 billion years of separate evolutionary history, the potential consequences of an uncontrolled biological encounter are simply unknown, which is reason for both caution and urgency. Caution in how we proceed, urgency in answering the life question before human missions make it permanent. The sun is nearly touching the horizon now. The Martian sky at sunset is extraordinary. It does something Earth skies do not. It shifts in a direction opposite to what you expect. On Earth, the sky near the horizon at sunset turns warm. Oranges, reds, pinks. On Mars, the sky near the sun at sunset turns blue. A pale, cool, ethereal blue arising from the scattering properties of Martian dust at low sun angles, while the rest of the sky remains its familiar amber rose. Blue near the sun, pink at the zenith. a reversal of everything familiar. As if even in this last moment of the day, Mars is reminding you that it plays by different rules, that it has always played by different rules, and that the story of what those rules produce, what they have produced in the past, what they might produce in the future, is still being written in rock, in ice, in chemistry, in the patient encoded language of a world that has been waiting, perhaps, for something capable of reading it. Night falls on Mars. It falls quickly, as it always does on worlds, without the thick atmospheric padding that softens Earth's transitions between day and dark. One moment the sky is pale blue near the western horizon, the remnant of the sunset's strange chromatic reversal. Then the colors fade. Then the stars begin to appear. And on Mars, the stars are extraordinary. Without the light pollution of any city, without the atmospheric moisture that softens and blurs the sky over most of Earth, without the comfortable haze of a dense world, the stars appear with a clarity and an abundance that is almost overwhelming. The Milky Way stretches overhead like a river of ancient light, a river that was flowing long before Earth formed, long before the solar system coalesced from its initial cloud of gas and dust. You sit down on a Martian rock, a rock that has not been touched since the solar wind last scattered dust across it, a rock that has been sitting in this exact position for perhaps millions of years, and you look up, and you try to comprehend what you have walked through today. 4 billion years of history, written in the ground you walked across, in the canyon walls you stood before, in the dried rivers and the ancient ocean floor, and the layers of ice that record climate oscillations stretching back beyond the beginning of complex life on Earth. A world that was once warm and wet and full of possibility. A world that through a cascade of interlocking geological and atmospheric processes lost the conditions for surface life and grew cold and still. A world whose internal heart still beats slowly and whose chemical complexity has never fully surrendered to simplicity. A world that still holds secrets. Perhaps the most important thing that Mars teaches us is not about Mars. It is about contingency. In philosophy and in science, contingency refers to the idea that things could have been otherwise, that the outcomes we observe are not inevitable, that the path history took was one of many possible paths, and that different initial conditions, different dice rolls in the great game of planetary formation would have led to different outcomes. Mars is contingency made geological. It is the path not taken. The warm, wet, magnetically protected, tectonically active, potentially life-bearing world that early Mars appeared to be heading toward, that world exists. It just doesn't exist on Mars. It exists here, 225 million kilometers away on average, orbiting slightly closer to the Sun, graced with a large stabilizing moon and active plate tectonics, and a sustained magnetic field. It exists on Earth, and understanding Mars, understanding precisely what went wrong, what cascade of events transformed a potentially habitable world into the ancient, silent desert we walked across today, is not merely an exercise in planetary science. It is an exercise in understanding what makes Earth possible, what makes Earth sustainable, what would need to go wrong, which cascade of events, which threshold crossed, which door closed for Earth to follow Mars's path. There is a reason that some of the scientists most deeply engaged in Mars research are also deeply engaged in Earth climate science. The tools are the same, the physics is the same, the questions rhyme, even if the specific answers differ. A planet is a system, a complex interacting system of geology and atmosphere and ocean and, in Earth's case, biology. A system in which each component affects the others, in which thresholds exist that, once crossed, are difficult or impossible to uncross. And the study of Mars is the study of what such a system looks like after a critical threshold has been crossed. It is, in this sense, an instruction manual, not a comforting one, but a useful one. Sit for another moment on this ancient rock, under this extraordinary sky, and feel, if you can, the deep time of the place. The rock beneath you was formed from volcanic lava billions of years ago. The dust around you was once part of that rock, ground down by billions of years of thermal cycling and chemical weathering, and the patient, relentless work of a Martian wind that has been blowing across this surface for longer than complex life has existed on Earth. You are surrounded by time in a way that is almost impossible to process emotionally. Not the time of human history, the few thousand years of written records and the 100,000 years of Homo sapiens, and even the few million years of our genus. The deep time of geology, the time in which mountains form and erode and form again, the time in which oceans appear and vanish, the time in which entire evolutionary lineages rise and fall without leaving a record that would survive long enough for anything to read. And yet here you are, reading it. Improbably, beautifully, here. A creature from the one world in the solar system that, so far as we know, has produced creatures capable of reading the geological record of another world. A creature whose existence depends on exactly the contingencies that Mars lacked: the moon, the tectonics, the magnetic field, the sustained warmth, and who has, against extraordinary odds, developed the capacity to travel across space and stand on the ground of another world and ask questions about it. That is perhaps the most remarkable thing about this walk. Not the canyon, not the ancient ocean floor, not the methane mystery or the subglacial lake or the sealed sample tubes waiting for a return mission. The most remarkable thing is that you are here, that anything capable of wonder is here, in the cold and the silence and the dust of a world that did not, as far as we know, produce its own wondering creatures. Something from the world that did came to look, to try to understand, to attempt the patient, humble, endlessly complicated work of asking, what happened here? The stars wheel slowly overhead. Phobos rises in the west, the larger of Mars's two small moons, a captured asteroid, lumpy and dark, crossing the sky faster than any moon moves on Earth, so fast that it rises and sets twice in a single Martian night. Its shadow, faint and elongated, passes across the dust around you, and in the sky, among those extraordinary stars, there is one that is slightly bluer than the others, slightly brighter, a pale blue dot, to use the famous phrase, barely distinguishable from a star, requiring knowledge and attention to identify, but there, home, watching from 225 million kilometers away, on average, sending its light across that enormous distance. Arriving here at the surface of Mars at the speed of light 12 minutes after leaving, a 12-minute delay. The time it takes for a message from Earth to reach Mars. The time it takes to be told that something has happened after it has already happened. A 12-minute reminder of how far you have come. Of how extraordinary the act of getting here was. Of how much of the universe remains between one small, warm, living world and the ancient, silent, magnificent world we have been walking across all day. Stand up. Brush the rust-colored dust from your hands. Look up one more time at the sky full of stars, more stars than you have ever seen or will ever see from the surface of Earth. And allow yourself for just a moment to feel the smallness and the largeness of it simultaneously. The smallness of any individual life against the scale of 4 billion years of Martian history. The largeness of the fact that life somewhere produced something that came to look at it and feel the weight of what was lost here. Mars does not ask for mourning. It asks for attention. And in the great silence of this ancient world, you have given it yours. That perhaps is enough. That perhaps is everything. Walk gently. The dust here is very old.